All right, welcome to video 3 of the definite integral. And today we are going to actually get to what we mean when we say integral. So let's talk about this integral, which is the area under this curve between A and B. And we are going to split this up into n rectangles. And we are going to say that x sub I is any point on the interval. Actually, I'm going to change that and say on the subinterval I. So we're going to be splitting this up into n rectangles, and each of them is going to be given a designation. N1, N2, N3, N4, rectangle 1, rectangle 2, rectangle 3, rectangle 4. Now, the width of each rectangle is just going to be the width of the region divided by the number of rectangles into which we split it. And so let's look at what we've got here. Our first rectangle has height f of x sub 1 times the width of the rectangle. Our second rectangle has height f of x sub 2 times the width of the rectangle. Notice they're all the same width, so we've got delta x for the width of every rectangle. And the area of this whole thing is going to be the sum of all these rectangles, dot, 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 all the way to f of x sub n times delta x. So if we want to write this as a Riemann sum, as the sum of the rectangles using our summation notation, oh, by the way, area equals there. Our Riemann sum for this would be the sum from I equals 1 to n of f of x sub I delta x. Now, the area under this curve is the sum of all of these rectangles, and we can pick or choose as many rectangles as we want. But remembering that the more rectangles, the more accurate, we could say that the area, the actual area, equals the limit as n goes to infinity. In other words, an infinite number of infinitesimally skinny rectangles of the sum of I equals 1 to n of f of x sub I delta x. Notice the similarities between derivatives and integrals. If I jump back to my derivatives, the limit as h went to 0, and now we've got the limit as we could say as delta x goes to 0, but instead we've said as the number of rectangles becomes infinite, as n goes to infinity. So, a definition. Given some function f, it is a defined function on some interval ab. The change in x is b minus a divided by the number of rectangles for n equal sized intervals. And x sub I is some point on the ith subinterval. The definite integral of f on AB and this is how we write the notation of the definite integral, is equal to the Riemann sum, the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x. This is our integral notation right here. This means the sum as we take the limit as n goes to infinity. These two numbers here, a and b, are our limits of integration. A at the bottom, b at the top, from left to right. F of x is our integrand. It is the function that we are taking the area under. And dx, notice that dx, this tells us what our variable of integration. But notice that it's also, notice the similarity between delta x and dx. Dx just means that we're taking a delta x that is a limit as that goes to 0. Just like on the derivative, we started with delta y over delta x, changing y over changing x, and when we took the limit, we said dy dx because it's an infinitesimal change. Okay, how do we say this? We say it as the integral of f of x from a to b with respect to x. And we'll talk a little bit more about that, but that is the definition of the definite integral. And we'll come back in the next video and we'll have some examples of how to write these and what exactly we're going to be doing with this integral. Key thing to remember though right now is that this notation here, this symbol right here, means the area under the curve from A to B, the exact area, just like the derivative with respect to x meant the slope of the line at a tangent point. Okay,